Hello there. Welcome to the third video in my functional analysis series. Today we're talking about continuity and discontinuities. And so what does it mean for a graph to be continuous, and what does it mean for a graph to have discontinuities? Now there is a very technical definition that regards continuity in the terms of understanding limits. Now that's calculus stuff. I'm just kind of going over a rudimentary layman's terms definition of what continuity is. And I always like to think of continuity. We want to look for the intervals of the x values in which the graph can be traced. That is, where can we trace along the graph with our pen without lifting it up? So the points where we can trace along it would be where it's continuous, and the points in which we have to lift up our pen would be where it's discontinuous. Okay. However, sometimes the discontinuities will be easier to identify. What I like to do is start with the assumption that a function will be continuous over all real numbers. That would be the interval of negative infinity to infinity. We're talking about interval notation. But then we take that and we break it up based on where we see the discontinuities. Okay. One final note before we get started, a lot of the time domain and continuity are the same functions. It's not all the time, but it's most of the time. In which case, what I like to do in those cases is look at domain, write it out, and then kind of mention that the continuity is the same. We'll be looking at both today though. All right, let's talk about this first graph. Let's talk about what the continuity is. Okay, and then let's talk about where the discontinuities are. So again, the idea of continuity is the idea that I can trace along the graph. So I'm going to choose a different color so I can trace along it. Doesn't need to be perfect. And I can lift up my pen, but now I've gotten to a hole. This is a part where I have to lift up my pen, and I have to then drop it back down after the hole to continue tracing. Okay? So that means we have a discontinuity at 1, 2, 3, at x equals 3. Now, you could write out the full coordinate pair of where the hole is. I usually just get used to writing out the x value, and you'll see why when we get into other examples. So this means we have a discontinuity with a hole at x equals 3. Okay? Continuity, so that means continuity. So this means we take the interval, I'll just put my scratch over here. We start the interval with the assumption that we're going from negative infinity to infinity. The key of understanding that is that we have these arrows at the end. And while they are pointing downwards, they are also ever so slightly pointing to the left and to the right, which means we can encompass more and more x values. However, we know we've got that x value at negative 3, so this can't be our interval of continuity. Instead, what I'll do is start with negative infinity, again, because we have the arrow. But then I had to stop at 3, so I'm going to write a 3 here, and then I'm going to write a parenthesis because the point is not defined at 3. And then, if you remember interval notation from my previous two videos, the union, and then I pick right back up after 3, and then I go to positive infinity. So this is what I mean by taking the real number line and breaking it up into smaller fragments. I've got one discontinuity that breaks it up into two intervals. So my answer for continuity is negative infinity to 3, and then 3 to infinity. Now, this is where I happen to bring up domain. So domain and continuity, I said sometimes they can be the same. In fact, a lot of times they can be the same. Is that the case in this instance? And the answer is yes. We do not have a defined point anywhere at x equals 3. So the domain is the same as the continuity. It would be the same answer. If I gave you this graph on a test and you asked, or you were asked, what's the domain and what's the continuity? For this graph, you would put the exact same thing down. Okay? Now, where does this kind of come up in functional analysis? Well, a lot of these functions are generally rational functions. Again, something we'll talk about in the future, but this is mainly where they'll appear. So, okay, let's go ahead and look at the second example. Okay, now what we're looking at is what is called a piecewise function. We have a nice general smooth curve to begin with, and then we have a jagged thing after this discontinuity. We can see, again, if I trace along it, I'll trace along with my pen, but then when I get to this hole, I have to stop, and I have to pick up my pen, and I have to drop it down at this point, and then I can continue on my merry way. Okay? So what happened there? That was at x equals 2. So our continuity and our discontinuities, again, where is the graph continuous? And not only where, but what are our discontinuities? So we identify the discontinuity first, and this is a jump. And this is primarily why I like to keep consistent with just stating all discontinuities and their x values. Because if I wanted to list a point, do I list this one here where it started? Do I list one here after where it ended? I mean, it's kind of a blurry line. So I just say jump at x equals 2. Okay, great. So continuity, again, we're taking that idea that we got the arrows. We're starting with the real number line. Okay? But again, we're not continuous. We had that point where we had to lift up our pen. So that's not our continuity. We'll start with negative infinity, and then we had to lift our pen up at 2. We'll close the parentheses, we'll write the union sign, and then we'll pick back up after 2 and go to infinity. And so that's what our continuity is. Negative infinity to 2, union 2 to infinity. So let's go ahead and talk about domain. Now, would domain be the same in this instance? And the answer is no. Actually, domain, we can say that there is a point defined right here at x equals 2. If I plug in x equals 2 into this function, I'm going to get a point off this graph. So from a continuity perspective, yeah, the graph is still broken up. However, there's no value I can't plug in and get a real number solution out of this. So this answer is that our domain simply goes from negative infinity to infinity. And this would be an example where the domain and the continuity are not the same. This defined point here sort of fills in that gap. Again, it doesn't fill it in from a technical standpoint because we can still see the jump. But this would be an example where the domain and the continuity are not the same. Let's go ahead and look at number 3. So again, we're looking out for continuity first. Again, in future videos, we look for domain first and then only look at the continuity if it's different. But since this video is about continuity, we'll look for continuity first. Continuity and discontinuities. All right. We'll go through. We got our arrows again. So we'll trace along it. And then we get to that hole, one more hole. We have to lift up our pen, and we have to drop it back down on this point. But then we have to pick it back up again to continue. So this is where I kind of shrug and go, how do we classify this? Is this a jump? Is this a hole? I'll let you be the decider of that. Comment down below what you think this should be called. Should this be qualified as a jump or a hole? For now, I have it listed in my notes as a jump, because technically we do have to lift up our pen and drop it down at that point and then pick it back up to continue. So a jump at x equals 5. Okay. So once again, let's take the continuity. We'll break down this. We have the arrows at either end. So we start with the idea that we're using the real number line to discuss continuity. Okay. But we had that jump. Okay. So we start with negative infinity. We go to 5. And we put our union sign down, and then we go from 5 to infinity. Now note that graphs can have more than one discontinuity. It could have 3, it could have 4, it could have 4, it could have infinitely many. In which case we'd have to find a way to consolidate our answer. We're just looking at the types of discontinuities in this video. So if you'd like to see a video with graphs with multiple discontinuities, make sure to leave that in the comment section down below. So we got negative infinity to 5 union 5 to infinity is our final answer. Now, if you understood the last example, this is where, again, domain will be different. If we just had that hole there, then this looks exactly like the similar situation to the first graph we looked at. However, we did have that point there. So we've kind of, again, filled in the gap in our domain. So for our domain, we can say negative infinity to infinity. Last example. What we have here is a graph with what is called a vertical asymptote. A vertical asymptote is when you see behavior generally like this. So again, let's trace along it. I trace along it and I keep going up. I've got an arrow right there. So do I eventually connect over to this portion? Do I just keep going up? What happens? Well, the arrow indicates that I keep going. I'm never going to cross over. So what this does is creates an invisible barrier that, in this particular instance, at the y-axis, and it can be anywhere, where the graph can't cross over. It's like an invisible barrier, okay? This is called a vertical asymptote. So when we're discussing our discontinuities, and this is especially why I like to say just the x values. Now, we don't have a point where it's discontinuous. We have a whole line. Discontinuous, it's a vertical asymptote. I'll spell that out first, but I usually just write VA. Vertical asymptote at x equals 0. The y-axis is where x equals 0. But once we get past that vertical line, once I just call it quits, pick up my pen and drop it back on the other side, I can continue on my way with this function, in which case my graph continues. So again, continuity. Let's write our little scratch work. Oop, not negative 8, negative infinity to infinity. But again, we have that discontinuity, so this can't be our answer. Well, where was the discontinuity? It was at 0, so we'll approach this the same way. 0 to infinity. Oop. Continuity is from negative infinity to 0, union 0 to infinity. Now, the question is, how does this affect the domain? Well, unless we plot a point on the y-axis somewhere, which we don't have, the domain, when you have a vertical asymptote, will always be the same. So the domain is the same as continuity. So again, if you were to get this question on a test, ask what's the continuity and what's the domain, you would write the same answer for both. And that will always be the case with vertical asymptotes. Okay? These appear a lot in rational functions. However, they can also appear in trigonometric and logarithmic functions and even piecewise functions. So in the future, again, I'll say it one more time, we'll be looking primarily at domain, and we'll only really be looking at continuity if the domain and continuity are different. But we've seen a couple examples where the domain and the continuity are the same. Go ahead and leave a comment in the comment section if you like this video, like and subscribe, and I'll see you for the next video. Thanks for watching.